Here is a question that sounds like it should have a simple answer. How long is the coastline of Britain? So you look it up, and immediately something is wrong. One government source says about 11,000 kilometers. Another respected source says more than 19,000. That is not a small disagreement. It is a gap larger than the distance from London to Tokyo, for the edge of a single island that has not changed size. Nobody made a mistake. Both numbers are correct. Because it turns out the coastline of Britain does not have a length. Not a real one, not a fixed one. And once you understand why, you will see that the same strange truth is hiding inside your own lungs, in every tree, in lightning, in the broccoli on your plate. This is the coastline paradox, and it quietly broke one of the most basic ideas in all of geometry, that any shape you can draw must have a measurable size. To see where the problem comes from, imagine measuring the coast yourself. You start with a giant ruler, say 100 kilometers long. You walk it around the island, laying it end to end, and you get some number. But a 100-kilometer ruler is enormous. It steps right over every bay and every inlet, cutting straight across them like a tightrope. So you try again with a shorter ruler, say 10 kilometers. Now you can follow the larger curves you skipped before, dipping into the big bays, and your total length goes up. So you shrink the ruler again, down to 1 kilometer. Now you trace around little headlands and coves the 10-kilometer ruler ignored. The length goes up again. Here's the crucial pattern. Every time you use a smaller ruler, you measure a longer coastline. A man named Lewis Fry Richardson noticed exactly this in the 1950s, almost by accident, while studying the lengths of borders between countries. The shorter your measuring stick, the longer the border becomes, and it never seems to settle down. Now you might expect this to stop. With a normal object, it does. Measure a circle with smaller and smaller rulers, and the length closes in on a single number, its circumference. The rulers get more accurate, and the answer settles. But a coastline never settles. Zoom into a bay, and you find smaller bays inside it. Zoom into those, and there are inlets, then rocks, then pebbles, then the rough grains on a single stone. At every level of zoom, new detail appears, new wiggles to trace around, new length to add. With a ruler 1 meter long, you would crawl around individual boulders. At 1 centimeter, around grains of sand. There is no point where the coast becomes smooth. And so, mathematically, as your ruler shrinks toward zero, the measured length grows without limit. It heads toward infinity. A finite island that you could walk around in a few weeks has an edge with no finite length at all. If that feels impossible, let's build a shape where we can prove it, exactly, with no fuzzy talk about rocks and sand. Start with a simple triangle. Now, to the middle third of each side, glue on a smaller triangle. The outline gets a little spikier and a little longer. Now do the same thing again to every straight edge you just made. Middle third, smaller triangle. And again, forever. This is the Koch snowflake, and here is where it becomes genuinely strange. Every single step multiplies the total perimeter by 4/3. 4/3, again and again, forever. That grows without bound. The perimeter is infinite. But the entire snowflake fits neatly inside a circle you could draw around the original triangle. Its area is finite. Provably, it is just 8/5 of the area of the triangle you started with. So here is a shape, sitting on your screen, with a finite area, enclosed by a boundary of infinite length. That is not a trick or an approximation. That is exactly what a coastline is. So if a coastline isn't really a length, what is it? This is where a mathematician named Benoit Mandelbrot had a revolutionary idea in 1967, in a paper with that exact title, How Long is the Coast of Britain? He realized we had been asking the wrong question all along. A straight line is one-dimensional. A filled square is two-dimensional. We assume everything is one or the other, but a coastline is too wrinkled to be a simple line and too thin to be a solid area. It lives in between. Mandelbrot gave these in-between shapes a number he called the fractal dimension, and it does not have to be a whole number. A smooth line has dimension exactly 1. The wild, jagged coast of Britain has a fractal dimension of about 1.25. The rugged coast of Norway, slashed with fjords, is even higher, around 1.5. The number measures roughness itself, how aggressively the shape fills the space around it. Mandelbrot named these objects fractals, and with that single idea, a whole hidden category of shapes snapped into focus. And once you can see fractals, you find them absolutely everywhere, because nature loves them. The reason is beautiful. A fractal lets you pack a nearly infinite surface into a finite space. Look at your own lungs. To absorb oxygen, they need enormous surface area, but they have to fit inside your chest. The solution is a fractal. Tubes branching into smaller tubes, branching again, more than 20 times, until the total surface area inside your chest rivals a tennis court. Your blood vessels do the same, reaching every cell in your body. So do the branches of a tree and its roots, maximizing contact with sunlight and soil. A bolt of lightning forks in fractal branches as it claws for the path of least resistance. River networks, snowflakes, mountain ranges, the florets of broccoli, the rings of Saturn, all built from the same simple rule, repeated at every scale. Mandelbrot's insight was that the messy, irregular world is not formless at all. It is fractal. The smooth lines and perfect circles of old geometry were the real exceptions. So how long is the coast of Britain? The honest answer is that the question has no answer. It depends entirely on the size of your ruler, and there is no ruler that is correct. This is not just a curiosity. It is why countries genuinely disagree about the lengths of their own borders, with neighbors publishing numbers that differ by thousands of kilometers, each measured at a different scale. A simple, innocent question, how long is this edge, turns out to have no bottom. And the lesson reaches further than maps. Some things in our world do not have a single number waiting to be discovered. They look different, and they truly are different, depending on how closely you choose to look. The coastline was never hiding its length from us. It simply never had one. This has been actually rendered, where we show you how things actually work. If this changed the way you see a map, you know which button to press.